So let's talk about Matroid connectivity. I'm going to tell you a little today about why Matroid connectivity is special. Now, as you know, with Matroids, there are a lot of equivalent axioms that we can use to talk about them. That's one of the nice properties that Matroids have. And when we're talking about connectivity, I think that the nicest axiom system to use is circuits. You can say that a Matroid is connected if for every two elements there's a circuit that uses them. Now, an equivalent way of saying that is for every two elements, they're in a U12 minor of the Matroid. You just delete the rest of the Matroid except for the circuit, contract everything but those two elements, and there's your U12. So what I've been doing with this project is I've been working with this definition, this concept called in-connectivity. Now this is in-connectivity with a capital N, not a lowercase n, so you can put the other one out of your mind. A Matroid is in-connected if for every pair of elements, there's an n minor that uses them. So like I was saying with U12, if a Matroid is U12 connected, then it's just connected. Here's a slightly less trivial example. If a Matroid is U23 connected, every two elements of the Matroid are in a triangle together. So the Matroid has to be connected. It has to be simple because if you have elements in parallel, they won't fit in a triangle. And it turns out that's sufficient. U23 connectivity is just connected and simple. So I promised you I'd tell you why Matroid connectivity is special. First, let me remind you some things that we like about Matroid connectivity. It's good because we can partition the ground set into components that has a really obvious presentation as graphs, maybe a not so obvious one as vector spaces, but it's nice. And if you were paying attention to Amanda's announcement, we have this theorem due to Tutte that if a Matroid is connected, you can take any element in the ground set, delete it or contract it. One of those minors will also be connected. So that's great. It's very useful for doing proofs by induction. So one of the questions that I wanted to know is, can we get these two properties here to apply for n connectivity when n is not U12, when n is something else? And the answer, it turns out, is no. We can't get both of them to hold for other Matroids. So let's get into that a little bit. First, I want to talk about the components. Another way of saying we can partition the ground set into components is to say, well, if we have an n minor using EF and an n minor using FG, then there's also an n minor using EG. When this happens, we say that the Matroid has the transitivity property. So in order for this to work, the Matroid has to be non-simple. If you take the Matroid n, well, n is n-connected, obviously. If you extend n, so take some element E that's in your Matroid n, put in a new element F in parallel with E, we can guarantee that F will be in an n minor. You just delete E. And we can also guarantee that if n is simple, then EF can't be in an n minor together. So n has to be simple. By the same argument, it has to be non-simple. It also has to be non-cosimple. So I'm going to interrupt this and give you another example. MW2, the two wheel, James calls this one the forgotten wheel. You can characterize MW2 connectivity by saying that the Matroid is connected and non-uniform. We can always get two elements in a Matroid like this, as long as it's non-uniform. So it turns out that we're going to have the transitivity property if and only if our Matroid is U12 or MW2. You can talk about connected components and connected and non-uniform components. Here's a little idea of how that works. I mean, since the matroid has to be non-simple, non-cosimple, it has some series pair, which I've drawn as this graph going out of the matroid. So you can extend, put in element C in parallel with A here, and then delete something from the rest of the matroid. Then you can co-extend, put D in series with C. Now, if the rest of this matroid is empty, right now we have MW2. And if it's not, we're going to keep going with this process of building this fan-like structure, and eventually we'll get something we can show doesn't have the transitivity property. So that other thing that I wanted to talk about, the minor induction property that Tutte gave us, there's only one connected matroid it works for, and that's U12. If we allow ourselves to consider disconnected matroids, we also pick up U02 and U22. These are the only three matroids that have this property. So I'll spare you the details of that proof. You don't have to read this. But for the connected case at least, the idea is we show that our matroid can't be simple, it can't be cosimple, and it can't be uniform. And the only matroid that satisfies that is U12. So I've talked about all the two-element matroids except for one of them. So I'll give you the result for that too. When you have a loop and a co-loop, U01 and U11, we can characterize U01, direct sum U11 connectivity, by saying no two elements are clones. Clones are the only time we can't get one to be a loop and the other to be a co-loop by minor operations. So that's it.
Any questions for Zach? Think there is any hope for doing this in the clutter connectivity case?
I was wondering about that. Well, it was said that duality doesn't quite work as well for clutters. So I'm not sure how it would work for applying this definition of connectivity either.